we go.
All right, so we left off talking about density. There's 3 questions you could be asked about density. What is the density, what is the mass, and what is the volume? And we discussed that the volume is usually the hardest one to isolate, that you make the most mistakes with. So remember, when you're rearranging density equation, get volume off the bottom. Move it up, get an equation where everything's on the top, and then you'll easily be able to see volume equals mass divided by density. Okay? And that goes for a lot of these algebraic rearrangements. Especially when we get in chapter 9, the gas laws, we're going to have a lot to deal with. Okay? Moving variables around all over the place, and you need to make sure that you're doing a sufficient job of isolating the variable you want, okay, correctly. Okay, so here's some common densities. Air obviously has a very low density, 0.001 grams per milliliter, a gram per centimeter cubed. Ethanol, 0.79. Water is 1. So ethanol is lighter than water. So if you put those two together without mixing them, just layered one on top of the other, ethanol would be on top of the water. And you can see some of these others. Gold, it's pretty heavy. Osmium as well. Okay. So mercury is 13.9. It's a liquid. So brass is actually lighter than mercury. So if you put liquid mercury in the bottom of something and put a brass nut on top of it, it'll actually float on top of the mercury. It wouldn't sink in it because the brass is lighter than the mercury, which is also a metal. It's just a liquid at room temperature. It's the only metal that is a liquid at room temperature. Okay, so a piece of gold has a mass of 301 grams, a volume of 15.6 centimeters. Wow. That image is too high. Calculate the density, okay? It's the only thing you can calculate, right? How do I know that's what the question is? Because of the information they gave me. That's right. Mass and volume. So density equals the mass over the volume. Okay? So density equals, this one's very straightforward, 301 grams for every 15.6 centimeters cubed. Okay? So what is the density of the gold here? Sorry? 29. 29. Now, how many significant figures should I keep in my answer? 3, right? Because how many do I have here? 3. How many are here? 3. So my answer should have 19.3 grams per centimeter cubed. 3 significant figures. Okay? The significant figures for that were easy to count. There's no questionable zeros. Okay? All right. Was there a question? No? The density of mercury, the only metal that is liquid at room temperature, is 13.6 grams per milliliter. Calculate the mass of 5.5 milliliters of the liquid. So what am I solving for? Mass. My equation is density equals mass over volume. On your reference sheet, that's the equation you get. So that's the one you're starting with. So what is the equation? From that equation, what is the equation to solve for the mass? Yeah. Okay. All right, so here's my density. Here's my volume. So mass equals 5.50 milliliters. Now, what if this was in liters instead of milliliters? Could I just multiply those two things still? No, because the units wouldn't work, right? This is in grams per milliliter. This is milliliters. Now, if the density was in grams per liter, then I would have to change this to liters, right? I'd have to change it to liters to be able to calculate those two things. So 5.5 times 13.6 grams per milliliters. My units are working here, right? I'm solving for the mass, the grams. The milliliters are canceling. I'm being left with the grams. So 5.5 divided or times 13.6. What is the mass?
74.8.
Good. So 3 significant figures, right? 3 significant figures, grams. That's the mass of this amount of mercury. Good. All right, I want you guys to try this one. The density of pure solid copper is 8.94. What volume does 5 kilograms of copper occupy? Okay. Work that for a minute. Think about it. How are you going to solve for that? Oh, okay, well, is that what other people are getting? I haven't calculated it, but we'll set it up in a minute. 0.559 for the volume. I don't think that wouldn't be correct. What? Okay, let's look at it. So we have, what are we solving for? Volume. Density equals mass over volume. Volume equals what? Mass over density. Okay, that's what you should have been, that's the equation you should have been getting. Okay, volume equals, what is the mass here? 5,000 grams. 5,000 grams. Okay, how did we get the 5,000 grams? Good. 1 kilogram equals 1,000 grams. So if I have 5 kilograms, that's going to be 5,000 grams. Okay? And I'm going to divide it by my density. My density is 8.94 grams. And I'm going to put my milliliters up here because I would just divide by the milliliters, so that moves it up top. Okay? So I end up with the milliliters on top, which is what I want. My grams cancel. So 5,000 divided by 8, the volume is what? I'm sorry, not 8, but 8.94.
559.2.
559.2. I'm sorry. I have a really hard time hearing you guys.
It's 559.2.
Thank you. Okay, that's milliliters. Okay, so how many significant figures would you keep here? It's hard. There's really just one significant figure there, right? So essentially we should just keep one, which is kind of ridiculous. But they should have given us more. If they said 5 kilograms, they should have said 5.00 or something like that. But that's, I think that more reasonably they should have given us like 5.00. So let's go ahead and keep 3. Volume equals 559 milliliters. Okay, because we have 3 here also. Okay, good. So that's what you should be getting. So you got to convert it so that the units in the density and the units of the mass are the same units, so that you can do the calculation. Otherwise, the units won't cancel. You wouldn't be able to solve for the milliliters, okay, until you do that. Okay, 2 liquids, A and B, have densities 0.75 and 1.14 respectively. When both liquids are poured into a container, one floats on top of the other. Which liquid is on top? Which one's lighter? This one, right? A. So A is on top. How many kilograms of mercury would fill a 5-liter container if the density of mercury is 13.6 grams per centimeter cubed? Okay, so go ahead. I want you guys to work on that one. How many kilograms of mercury would fill a 5-liter container if the density of mercury is 13.6 grams per centimeter cubed? Think about what you're going to have to do. Number 1, think about, what am I solving for? Make sure that everything's in the correct units, and then answer the question. I will tell you this. 1 centimeter cubed equals 1 milliliter. They are equivalent. Okay? Okay, let's see if we have a consensus out there. What is, how many kilograms? 68. Say it again. I'm sorry, I just didn't hear. 68?
Yes.
68 kilograms? Is that what people are getting? Anybody else getting something else? No? Okay, good. So You would have to solve for the mass. Mass equals density times volume. Density is 13.6 grams per milliliter, let's just say, okay? And times 5,000, I'm sorry, going the wrong way. Yes, no, that was right. 5,000 milliliters, okay? My milliliters cancel, I'm left with grams. Once you find your grams, then you convert to kilograms, right? So grams converted to kilograms. From the grams, there's 1,000 grams in every 1 kilogram. Okay, so if that's the procedure, if you were following or something about like that, then you'd be able to get the answer. Okay? Any questions? Great. So it's really important that you guys look at what conversions need to be made. Because it's not always so straightforward. All right. So let's look at some of the experimental quantities you'll encounter in chemistry. Things like temperature. Okay. There are 3 temperature scales: Kelvin, Celsius, Fahrenheit. Fahrenheit is basically useless to us, but there is a way that you can, if you're given the temperature in Fahrenheit, you can convert from Fahrenheit to Celsius, and then from Celsius to Kelvin if you needed to. Okay, so there are conversions between all 3 of these. This has a very simple conversion. Okay, if you'll notice, 0 degrees Celsius is 273 Kelvin. Okay, if I go up 20 degrees, I hit 293 Kelvin. What's the difference here? 20. The difference here is 20. The difference here is 20. So the increase is exactly the same on each scale. Okay? If I go up 1 degree Celsius, I go up 1 degree Kelvin. They're simply just offset from one another. Because this Celsius scale is more based on the freezing point of water and the boiling point of water. Okay? The Kelvin scale is set more so that you can reach an absolute 0 temperature. Okay? So if I went to 0 Kelvin, that is absolute 0. That means there's absolutely no more energy in a system, and that's the coldest you could ever attain. Okay? Which is absolute 0. So that's what this scale is based off of. Okay, the Kelvin scale. Okay, and Fahrenheit is it's a terrible scale for us, but that's what we use here in America. So if you are measuring temperatures using Fahrenheit and you want to then use that in the laboratory, then you'd have to know the conversion for that, which is impractical. You just use a Celsius thermometer. But in any case, okay, so Kelvin scale is equal to the degrees Celsius plus 273.15. The easiest conversion you'll ever do, but you need to be very familiar with it. You'll need to know how to do it. That's not something I'm going to tell you again. Like, I'm not going to keep constantly reminding you of that. That's something I expect you to know. To convert from the Kelvin scale, you need to add 273.15 degrees Celsius. Okay? This would be given as a reference. You would have the reference material if you were ever going to convert from Fahrenheit to Celsius. And it would be through this equation. Okay? So Fahrenheit equals 9/5 of the degrees Celsius plus 32 degrees. Okay? And that'll get you back and forth between those two. Okay? Likewise, if I was going to solve for degrees Celsius from the Fahrenheit, then I would simply say I would subtract 32 from each side, minus 32, right, equals 9/5 degrees Celsius. And then I can multiply this times 5 and divide it by 9. And that would equal my degrees Celsius. Okay? So just know how to go between those, or how to do the algebra there. Okay. Solder is an alloy made of tin and lead that is used in electrical circuits. A certain solder has a melting point of 224 degrees Celsius. What is the melting point in degrees Fahrenheit? Okay. So we have degrees Celsius equals 224 degrees Celsius. Okay. And I want to go to Fahrenheit. So degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32. Okay? So what is the degrees Fahrenheit for that? Okay? 0.4? Sorry. 435? Okay. Okay, that makes more sense. Point what? 0.2. Okay, so 435.2 degrees Fahrenheit, which you would expect because the Fahrenheit scale would be higher than the Celsius scale. Yes? 437?
It's 225 and 224.
Yeah, it's on top.
Oh, it's because I wrote it wrong. So some of you are doing the actual question and some of you are doing my question. Okay, so, but, okay, you guys did it right. All right. Yes?
Did you apply significant figures to this?
Yes. So 3 significant figures, 435 or 437, whatever you came up with. Okay. Okay. Now, helium has the lowest boiling point of all the elements at negative 452 degrees Fahrenheit. Convert this temperature to degrees Celsius. So what is the Celsius temperature that would allow for the boiling of helium? Let's see if we can get a consensus on this one. Is anybody getting an answer?
I think. How much? Yeah, I'm way off. Yeah, that's all right.
Okay, that's the right answer. Yeah, I just Googled it. I know you're like, this is so worthless, Mr. You just Google it. Technology. Okay, but it's good to know in case you ever wanted to convert that.
Quick question. So
yes.
the two formulas
that you gave us, are we supposed to use the one with a K? Because I plugged in like Fahrenheit to the Fahrenheit formula and tried to solve for C.
Yes. So let's walk through it, okay? Okay. So first we take negative 452 degrees Fahrenheit, okay? And we would subtract 32 from it. Okay? Is that the first step? You guys are good with that? And that would equal 9/5 degrees Celsius. Okay? Now, what is that? Who has that? Negative 452 minus negative 420. Oh, I'm sorry. 6, 7, 8. 84, right? Okay. Equals 9/5 degrees Celsius. 484 times 5, that's the next step. So we're going to multiply it by 5. 5 times negative 484. Negative 2,420 equals 9 degrees Celsius. 9 times the degree Celsius. Okay, and divide that by 9, and you'll get your degree Celsius. Okay. All right. There will not be a lot of questions of that sort, but it's possible you get one or something. Okay. So you need to be familiar with how to do that conversion. That conversion will be on the reference material. Yes. Oh, okay.
It'll be on
You don't have to memorize that. No.
the Celsius form, the Celsius to Kelvin. Is that one?
You won't necessarily have that one. I expect you to know. Add 273.15. That's what I expect you to know for Celsius. It's just offset by that much. Okay. So try to learn that one. Remember it. The highest temperature ever recorded in Phoenix, Arizona was 122 degrees Fahrenheit. More Fahrenheit. All right, don't worry about those. I'm done with this Fahrenheit to Celsius nonsense. Okay. Let's talk about accuracy and precision. Okay. So this is just definition, but in the laboratory, you'll often be talking about how accurate something is or how precise something is. So what's the difference between those two things? So if you're in the laboratory and you're collecting data, then if your data points are all really close together and you've hit the target point that you were trying to, then that's accurate and precise. So you have both precision and accuracy in your data. So let's say you're in the laboratory, you're measuring the density of something. You know what the density should be, and you're trying to measure it and see how well you can get that density. Okay? If you hit the density and your data is all substantiating that because it's all very close together, then it's precise and accurate. Your method for finding the density is both precise and accurate. Okay? But if you measure the density and it doesn't hit the target density that you're trying to get, but your data is all at the same place, then you have precision but no accuracy. Okay, so your method for measuring this density is consistent, meaning that you're doing it the same way and it's giving you the same result, but something's wrong with it because you're not hitting your target. Okay? Now, if you measure it and you're all over the place, you don't have precision or accuracy. Okay? So that's the difference between these two terms. Accuracy, how close to a measurement is the true value. Precision, how close a set of measurements are to each other. Okay? So how close is that data to each other?
Is accuracy and precision always together? So you can't have just accuracy and not precision?
No, you can have, if I'm not trying to hit a target at least I have precision in my data. So what if I don't know the target? And that's more just, am I precise? Am I doing this again and again consistently? And so, no, they can be separate. Yeah. Less so accuracy if you're doing repeated. If you just do it one time, then did you hit it? That's accuracy. Because there is no precision because you haven't done you haven't done it multiple times. Okay. Okay. Now, dimensional analysis is a very important method to calculating your desired result. Okay. So it's very important that you know what is the unit you're trying to get, and what are all the other units you have, and how are you going to cancel out those other units so that you obtain the one that you want. That's dimensional analysis. Okay? You're given a unit. Your desired unit is what you want to get. That always goes on top. The thing you're trying to get rid of goes on the bottom so that it cancels and you'll end up with your desired unit. Okay? And we are going to be practicing a lot of dimensional analysis in here. We did some of it already with density, making sure our units were the same, and canceling out the things we wanted to get rid of, keeping the ones we want. Yes?
If you can go back real quick.
Sure. Absolutely. Okay. Okay. So lengths of 1 meter, 1 yard, 1 centimeter, 1 inch are shown, as well as comparisons of 2.54 centimeters and 1 inch, and 1 meter and 1.094 yards. Okay. So we have these different units, and sometimes you have to be able to convert between one and the other. So let's say you were given 375 centimeters. You were told, this is 375 centimeters. And you want to know what that is in inches. So if you look here, it shows you that 1 inch, this is 1 inch, okay, and that blown up to scale, 1 inch is equal to 2.54 centimeters. That's the information you need to be able to go from inches to centimeters. Okay? This equals this. So now I can create a conversion factor. A conversion factor is the ratio that you need to multiply this number by to end up with your desired result. So before I put any numbers into my conversion factor, I'm simply going to set it up. Okay, I always start with what I'm given. What is the unit on top that I want to get? 2 inches, right? What is the unit on the bottom that I want to get rid of? Centimeters. My centimeters will cancel, and I'll be left with inches. Now I know what numbers to put here. I know which number goes on top, and I know which one goes on the bottom. The number for inches goes on top. The number for centimeters goes on the bottom. 1 inch on top equals 2.54 centimeters. Okay? What we just did is how you would convert anything. It doesn't matter what it is. Anything that you want to convert, you do it in this way. Okay? In the kitchen, you want to convert cups to ounces or gallons to liters. Whatever it is, you do it in this fashion. You always start with what you're given. You cancel that out and you end up with what you want on top. Okay? So in that way, we will be converting a lot of things. We'll be doing a lot of dimensional analysis and conversions in here. Okay, this is just showing you how the National Institutes of Standards and Technology maintain what certain volumes or masses are. So if you think about it, what is a gram? It's a measurement of matter, right? So 1 gram, if I weigh out 1 gram on my scale, it's because that scale has been calibrated to say that when this amount of matter is on top of the scale, that's 1 gram. Okay? Well, how have we determined how much matter is 1 gram? Well, this is 1 gram. At the National Institutes of Standards and Technology, they have an exact calibrated piece of metal that is exactly 1 gram. So if I go to the moon with my scale, does the mass change? So let's say I weigh myself here on Earth, and then I go to the moon and weigh myself. Do I weigh the same? No. Has my mass changed? No. My mass has not changed. My weight changed, but my mass did not change. The amount of matter that is inside of me is the same. So how could I make it so that I weigh the same on the moon as I do here? I use a standard. If I took this to the moon and I calibrated all the scales on the moon to say that this is 1 gram, then when I stepped on the scale, would I weigh the same as I do here on Earth? Yes, right? So this is a standard. That's how we use standards so that we know exactly what is 1 gram, right? Because it's arbitrary. Okay? Just like length and anything else is. Okay, we've already seen those. Volumes. Volumes we measure mostly in milliliters. Here's a graduated cylinder we would use in the laboratory to measure milliliters or liters of substances. Okay? And that is something that you should be familiar with, how to convert between milliliters and liters. 1 milliliter equals, you guys like to look at it this way. 1,000 milliliters equals 1 liter. Okay? Okay, here's an example of how you would determine the volume of something that you can't just measure the volume of. So this piece of rebar, okay, has all these rivets in it and stuff, and you can't just take a ruler and then measure every little crevice of it and find its volume. It would be too hard. Okay, so an easy way to find the volume is displacement. Here you have water to a specific amount. You drop the rebar in and it displaces it to a new amount. The difference between here and here is the volume of that piece of rebar. Okay, the water difference is telling you what the volume is. So now I could easily find the density of this. I could go weigh it on a scale, find the density. I could displace it in water and find the volume, and then I could easily determine the density of it, the grams per the milliliter. Okay, same idea here. Here's a piece of gold. You can displace it to find the volume because it would be impossible to know or measure the volume of that item otherwise. Okay. Okay, so now we're going to start into chapter 2. Chapter 2 is more fun than chapter 1 because we actually start talking about atoms and molecules and chemistry and okay. All right. So when we talk about the atom, it's good to understand the history of how did this idea of the atom even come about. So we have early philosophers, Aristotle, and things like that they have these ideas that matter, stuff around us, is made up of these tiny particles. Okay, but nobody could ever really substantiate that until Dalton came around, and Dalton started to do experiments to identify these parts of matter. Okay, so for example, he could undergo chemical reactions. He'd start with certain chemicals. He'd undergo those chemical reactions, get new stuff, and then he could break them apart again, decompose them back into their constituent elements. And so he's starting to identify some of the characteristics associated with these, how these chemicals come together. Okay, and he makes postulates. And so his postulates, the first one states that matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of an element that can participate in chemical change. Okay, so now he's identifying that this atom is what makes up matter, and on the atomic level, these atoms are the smallest parts of matter. Okay. His second postulate, it states that an element consists of only one type of atom. So here you have a copper metal, piece of copper, a penny. Okay, and you can see that that penny contains all these atoms that are all copper. They're copper, or if I go to Home Depot and get a copper pipe, that's copper metal. All the atoms in there are copper. And so he's postulating that matter is made up of these elements. And if you have a pure substance of matter, then it's made up of the same type of atom. Okay? So these elements consist of only one type of atom, which has a mass that is characteristic of the element and is the same for all atoms of that element. All right? So in his basic understanding, this is a very good postulate. Now, this postulate no longer holds completely true. And we'll see why. And that it has to do with the fact that, for example, copper. If we look here, if all the copper atoms had the same mass, then this would be a whole number instead of a decimal or a fraction. Instead of 63.546, it would be 63, or it would be 64. Okay? And we'll explain why. But not every atom of copper has the exact same mass. So he postulated that, but that's no longer completely accurate. Okay, it's a good postulate though. All right? So his third postulate, atoms of one element differ in properties from atoms of all other elements. Okay? So, absolutely. So, if I have sulfur, it's different than phosphorus, which is different than silicon. And they act differently. A compound consists of atoms of two or more elements combined in a small whole number ratio. Okay? So, whole number ratios meaning, here's copper 2 oxide. For copper 2 oxide, we have exact numbers of copper and oxygen. 2 coppers for 1 oxygen. 2 coppers for every 1 oxygen. All right? These come in these whole number ratios. Actually, it'd be 1 to 1. Copper 2 oxide, Cu. Okay? So 1 copper for every 1 oxygen. I guess they're just not showing it. Okay? But that would be the whole number ratio. And all elements come in whole number. You can't have half of an oxygen, right? You have to have a whole oxygen. So that's a good postulate. Atoms are neither created nor destroyed during a chemical change, but are instead rearranged to yield substances that are different from those present before the change. Okay? So this is great because he's seeing that if I put two things together, I'm going to get a new substance. That's a chemical change. These atoms are rearranging themselves, but they're not destroying themselves. So if I take hydrogen plus oxygen and I produce water from that, okay? If I produce water from hydrogen and oxygen, did the hydrogen get destroyed in the process of forming the water? No, it didn't, right? So it's still there. How did he know that it was still there? Well, he could decompose this back to H2 plus O2. So he could pull those elements back out. After he created this, he could pull them back out. So he understood, oh, they're still there. They're just rearranged. They're just in some different form, but they're still there. I didn't create it. I didn't destroy it. So the elements are not created or destroyed. They're just simply rearranged in the chemical reaction. Now, this postulate can no longer be 100% true either. For what we're talking about here, for what he could see and understand, that's absolutely true. However, there's what he didn't understand is on the nuclear level, you can have radioactive nuclear decay of elements. So elements can be destroyed and converted into other types of elements through nuclear reactions, nuclear decay, okay, which he didn't have any idea about. But this postulate is very good for what he could see. Just pure chemical reactions on this level, not on the nuclear level. That's absolutely true. Okay. Okay, so here's the law of definite proportions. It's showing us how these things hold true to be in these whole number ratios. Sample A, B, and C all have different starting masses. 14.82 grams of carbon, 22.33 grams of carbon, 19.40 grams of carbon. Okay? But the ratio of carbon to hydrogen is consistent. So here, different amounts of carbon and hydrogen. Okay? But if we look at the ratios of those, so 14.82 divided by 2.78, the ratio of that, okay? Or this divided by that, this divided by that, 5.33 divided by 1, 5.33 divided by 1. So they're in those exact same ratios, okay? So, so this is showing us that the composition of these would be the same from one sample to the other, okay? It's in definite proportions. Okay, now, so Dalton, he has these ideas of this atom. He's starting to postulate these ideas of what it is, what matters consists of. But they still don't understand, well, what makes an atom? What makes up an atom? An atom's an atom, and we have all kinds of different atoms, right, and different elements. But what makes one atom different from another atom? And what parts are the same about them? They didn't understand any of this. So J.J. Thomson, he creates this apparatus called an cathode ray tube. And he's going to use this to identify a subatomic particle. He doesn't know what this atomic particle is, but he takes his ray tube and he has two different electrical plates, and he's causing this subatomic particle to come off and shoot off of there in a ray. You can see it's like a green line coming through. And then he sets up two electric plates here. He has a magnet as well and electric plates. And he's going to try to identify some of the properties of this. So he takes the positive plate and he turns it on. Or let's say it's down here. And the beam goes towards it. Okay, he says, okay, so let's try the negative plate. He turns on the negative plate and the beam goes away from it. So what do you think is the subatomic particle that he's identifying here?
Electron.
The electron, right? Because if it's a negatively charged electron, negative plate pushes away, right? Positive plate goes towards it. It's being attracted. So that's what he's seen here. They've never seen this particle ever before. They have no idea what it is. He says, okay, this thing must be negatively charged. let's call it an electron. So now we have an electron. So now we know atoms, one of the subatomic particles of atoms is the electron. So there are electrons on these atoms. Later, Milken, he could measure the charges of these particles, and he was able to identify the charges of these electrons in certain things based on the size of the particle and and the charges, and he came out with the exact same number each time. Okay, so this data showed that each droplet had 1.6 times 10 to the 19th coulombs. Okay, this fundamental charge of an electron. So he's able to identify what the charge of an individual electron is based on this experiment. So this is their thinking. Okay, so they've discovered electrons, and later they did discover protons as well, kind of in a similar fashion. And so they're starting to identify, okay, we have electrons, protons. We know the charges of the electrons. We know the proton is also charged with an equal magnitude as the electron. Okay, but it's opposite in sign. And they think, okay, so we have electrons and protons. Just it's like a chocolate chip cookie, right? You have the chocolate chips all throughout, and the positive particles mixed throughout. So everything's ubiquitous throughout. Okay. So that was one theory. Another theory was you have the positively charged matter here, electrons around here. Okay. So to try to understand where actually the subatomic particles were on the atom, another scientist, Rutherford, comes along and he does an experiment. Oh, I have a link on that one. Let's see if I can get it to work. Right there.